All right, so today we're going to bring into our kind of understanding the way functions work, the idea of concavity. Now, concavity is kind of the first time we've assigned outside of, so position was the original function, velocity was the derivative of that function, and we always said acceleration was the second derivative. Now we're going to actually give a more, not necessarily direct, but we're going to introduce a concept to what does the second derivative actually tell you about any function, not just one that's dealing with, like I said, the position, speed, velocity, or sorry, position, velocity, acceleration. So concave up is where the function is increasing on an open interval. And concave down is where an open interval is of the derivative is decreasing. So concavity is based around the first derivatives changing. So this is why I said that we're going to introduce the idea of kind of assigning more meaning to the second derivative. So if f double prime is greater than 0 on an interval, then the graph of the interval is concave up. And then vice versa for concave down. It's less than 0. Now the key thing is if the function has a second derivative. If a function is only once differentiable, then you're just going to have to look at it and check on its concavity. It doesn't mean that there is no change in concavity, it just means you can't rely on the second derivative. But if it's first differentiable, then you can use the first definition. And the stupid way to remember the way they kind of look, concave up is a cup and concave down is a frown. So the concavity talks about, so like, you would say this function is concave up. And you would say this function is concave down. And what we're going to look at is where does the function change concavity. So like if I did like this function, you can see maybe about here. That one's a little bit obvious, but maybe about there. This part's concave down. So concave down. And then this part looks more concave up. So, and this is a much better demonstration than my attempted sketch. So x squared is a function that's always concave up because if we take its second derivative, so y prime is 2x and y double prime is just positive 2. So this function is concave up everywhere because the derivative is positive at every point. Versus if we look at y equals x cubed, then y prime is 3x squared and y double prime is 6x. So at 0, to the left it's negative, and to the right it's positive. So to the left of 0, which you can see here, it's concave down, and to the right of 0, it's concave up. Now, these are just two cases to where you can have no change in concavity, or you can have one change in concavity. Take a function like sine, that has an infinite number of times where it changes concavity across the whole x-axis. But you use the second derivative to determine where those points are. And then points of inflection are kind of like the critical points for second derivative. So remember, critical point was where the derivative was equal to 0 or undefined. Point of inflection is a point where the function has a tangent line and where the concavity changes. Now, key phrase there is has a tangent line. So remember, if it has a tangent line, that means that the slope exists at the point. So this is kind of implying that you've got to have it at least be differentiable at the point, because it's not enough to be continuous. Because go back to like a corner or a cusp. Those meet, but you don't have a tangent line, because at that point, if you approach it from one side, you get one value, and if you approach it from the other side, you get another value. And where the concavity changes. So one example of a place where it has a tangent line, but the concavity doesn't change, is x to the fourth. First derivative is 4x cubed. Second derivative is 12x squared. So if you look to the left and right of 0, though, this is positive on both sides. So just because the second derivative is equal to 0 doesn't mean that there's going to be a change in concavity. It's like x cubed. Its first derivative is 3x squared. It has a tangent line of 0 at 0, but it doesn't go from increasing to decreasing. X cubed goes from increasing to 0 to increasing once more. So critical points are related to first derivatives. Points of inflection you can start to associate with second derivatives. Now again, you need to have a tangent line, so it's at least got to have a first derivative there. Because without a first derivative, you can't have a tangent line, because remember, y equals mx, or y equals f prime of x naught. Let me just write it down instead of trying to talk it out. This old function. Without a first derivative existing, you can't find the tangent line here. You can find the tangent line from the left and the right, but remember, it's got to be the same at the point for it to be differentiable. So you need this tangent line, not two different ones. That's why it has to be not just continuous, it has to be differentiable is important. So these are a reminder, these dealt with your first derivative. So critical points go with first derivatives. Now the second derivative test for local extrema kind of puts the two derivatives together. So if f prime of c is equal to 0 and f double prime of c is less than 0, then it has a local maximum. Because this says that the slope is 0, and if it's negative, this is concave down, so you would have something like this. And then number 2, f prime is 0, you would have something like that. The problem is if both the first and the second derivatives are equal to 0 at the point, then your test fails. You don't have anything to go off of. This was the case of so take y equals x to the fourth. Once again, you have these derivatives, and at 0, all of these derivatives are equal to 0. So it doesn't tell you if there's a change in concavity or not. You have to actually check the second derivative. Same way as, well, sorry, that was the wrong explanation, or the wrong thing to lean into. The derivative is 0 at the point 0, and the second derivative is 0. And if it's not increasing and the concavity is not changing, that doesn't tell you anything about the function. You have to actually go and check and see, is it a local max, is it a local min, or neither. You know for x to the fourth, because it's a parabola that opens up, that is going to be a minimum. But just using the test purely, that doesn't tell you anything at this point. But these are just really nice tests to have to make life a little bit easier. So let's say you have this function, or you have the derivative and the second derivative. So you know the rate of change, and you know the rate of change of the rate of change. So what can you conclude? So remember, first derivative tells you how it's increasing, how it's decreasing. Second derivative tells you about, is it concave up, is it concave down? And we also know we go through the point 0, 4. So let's go ahead and mark that. So we have a point. And now let's try and mark this off. So I need intervals of increasing. I'm also going to need intervals, and I'll put the S in parentheses because we don't know if there's going to be multiple intervals of increasing or decreasing. We just know we're going to look for them. And then I also need where it's concave up, and I also need where is it concave down. So if we look at the first derivative, so this function is positive from negative infinity to 0, and then again from 2 to infinity. So remember, where the derivative is positive, the function is increasing. So from negative infinity to 0 and from 2 to infinity, the function's increasing. And then it's decreasing when the derivative is negative. So the only place where the derivative is negative is between 0 and 2. So this is where the derivative is greater than 0. This is where the derivative is less than 0. Now concavity, we just said if it's positive, then it's concave up. So it changes concavity at 1, and to the right of 1, it's positive. So this is where concavity is positive. And then from negative infinity to 1, our concavity is negative. So we have a point to go off of, or we have a couple of intervals to go off of. Now, I can't promise that I can draw the function exactly, but I do have a good idea of how it needs to look. So remember, concave down looks something like this, or even kind of like that. All I need for concave down is to kind of think like an upside down parabola, or a parabola that opens downward, I should say. So if I'm increasing from negative infinity to 0, and it's concave up, then that's going to be interesting to draw. So you can kind of think like with that, I need to keep that it's concave up to the right, but I need it to be concave down to the left. So it's not just going to be like, it's going to be like this point here is going to have to be at 1, and then whatever f of 1 is. Because notice this is kind of where it looks like it goes from opening upward to opening down to opening up. So if I try and sketch this, so I need to be increasing, 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 need to taper off, and then This is where you have to be careful. So I'm at 1. Now, granted, I didn't really hit the point directly, but it's pretty close. Then I need to start doing, the function is going to be decreasing, 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 decreasing to here, where the derivative equals 0 again. And then I can just increase again. So something along these lines. And if we break it up by our intervals, I'm increasing from negative infinity to 0 and from 2 to infinity. I'm decreasing between 0 and 2. So the function here is going down. And then I tried my best to do a split about here, which looks not half bad. Granted, it does help that I covered it up with a line to help kind of patchwork it together. But what I've got is to the left of that, of the point 1 at 1, it's opening downward because the second derivative was negative. And then to the right, it's opening upward because the second derivative was positive. So I've got a concave up and concave down where they need to be. But this is what you can use from just the information of the first and the second derivative. Notice, didn't have the function. The only thing I knew was the way its first and second derivative behaved. And I also knew that it went through the point 0, 4. So I had a little bit of information there. So now let's try, what can you look at, or what can you get from a function where now you kind of have everything to go off of. So here's the original function. So where are the zeros? Well, zeros are going to be at just x equals -1, and that has a multiplicity of 2. Are there any vertical asymptotes? So is the denominator undefined at any point? No, because it's 1 plus x squared. That's always going to be positive, so that'll never reach, or sorry, not never reach, that will never be 0. So none there. Horizontal asymptotes. So if we multiply this out, this would be x squared plus 2x plus 1. That will have a horizontal asymptote of y equals +1. Now, what about the second derivative, or the first derivative, sorry. So where is it increasing and where is it decreasing? Now, if you look at this, again, remember, we're looking for critical points here. Because I need to know where is the function, or sorry, where is the derivative undefined and where is it 0? Because that's going to tell me a little bit. So if I were to, so again, the denominator is never 0, but 1 minus x squared, so this is 2 times 1 minus x, 1 plus x, just the difference of squares. So I've got something I can go off of. So if I look between -1 and 1, so remember this is for f prime, If I plug in 0 to the original or to the derivative, I get 2 times 1 over 1, so it's positive. And then if I plug in, let's say 2, so this was x equals 0, we'll do x equals 2, and x equals negative 2. If we plug in 2, I get 2 times 1 minus 4, which is negative 3. The denominator is always positive, so this is going to be decreasing. And if I plug in negative 2, I get similar results again. Actually, I get the exact same result, to where this is 2 times 1 minus 4. So this one's also going to be negative. So let me clean that up just a little bit. So we go decreasing to increasing. So you do like that. So we have a maximum, or sorry, we have a minimum at 1. I'm going to need a little bit more room. I didn't give it quite enough room here. So this is negative 1. This is positive 1. So we have, for our local extrema, there's a minimum at x equals negative 1, because it goes from decreasing to increasing. So that would look like a opening up parabola. And then that goes from increasing to decreasing, so that could look like a opening down parabola. And we don't know if these are absolute. We don't know if they're relative. We just know there's a min and a max. Now if we check for concavity, let's take a look at and see, are there any points of inflection? So I'll switch over colors again. So this is going to have roots at x equals 0. And then you can think about this as x plus square root of 3 times x minus the square root of 3. So we'll have, here's 0, here's negative square root of 3, here's positive square root of 3. And what I can do from those, let's pick points that are going to be easy. Don't go for anything super challenging. So I'm going to pick x equals 1, 2, and then I'm just going to do the negative versions of those on the left-hand side. So to speed up with your calculations, don't even worry about the denominator, because the denominator is always positive here because it's 1 plus x squared. So when I talk about this, I'm only going to talk about the numerator because I've already ruled out the denominator coming into play for changing the signs for this problem. So if we plug in 1, we get 1 times 1 minus 3, which is going to be negative. If we plug in 2, we get 4 times 4 minus 3, which is positive. If we plug in negative 1, we get negative 1 times 1 minus 3, which is going to also give us, or which is going to give us a positive, because it'll be negative 1 times negative 2. And if we plug in negative 2, we get negative 2 times positive 1, because we're going to get 4 minus 3 here. So just to make sure I have enough room to write over here. Oh, I'm covering up my own stuff. So we'll check the absolute extrema here in a minute. So we actually have points of inflection at negative square root of 3, at 0, and at square root of 3 because the sign changes. So that means these are all points of inflection. So points of inflection at x equals negative square root of 3, 0, and positive square root of 3. And then we also have, here's a interval that's concave up, and then also square root of 3 to infinity will be concave up. 0 to square root of 3 will be concave down, and negative infinity to negative square root of 3 will be concave down as well. Because remember, concave down is where it's the second derivative, the interval where it's negative. So negative infinity to negative square root of 3 union 0 to square root of 3 is concave down. I'll write that over here. So we have concave down and concave up. So concave down from negative infinity, negative square root of 3 union square root of 3. Whoops. Not square root of 3. 0 to square root of 3. And then the remaining intervals, negative square root of 3 to 0, union square root of 3 to infinity, are concave up. And then if we want to know where's our function increasing, it's increasing from negative 1 to 1, and it's decreasing from negative infinity to negative 1, union 1 to infinity. Now the absolute extrema, we know that if we're going to have them, they're going to be on 0, 1. Or they're going to be at either negative 1 or 1. So notice also where our local minimum occurred. So notice it was at negative 1. We knew that was a critical point because the derivative changed directions. But if we want to confirm that it was a minimum, notice at negative 1, which we knew is where the derivative equaled 0, at negative 1, the concavity was positive, which means the derivative equals 0. It has a positive concavity, which means it's concave up, which makes it a min. That's what the concavity confirms local extrema is referring to. Now, in terms of are they the absolute extrema, you have to go to the actual function. Because if you look here, now, of course, having the graph is a little cheating, but if you didn't have the graph, keep in mind the way that it's going to work. We are increasing notice we're decreasing from negative infinity to negative 1. Because you don't read it right to left, you read it left to right, so you say that it's decreasing to here. Remember, we have our horizontal asymptote, and we want to know, okay, did it ever cross it? If you want to know if it crossed it, this is how you would check. You would set 1 is equal to the original y function, and you would find that the only place that it actually crosses is here at x equals 0. That's the only time it equals 1. And so, because it only crosses it at one point, and it's constantly decreasing to the right, that means it's decreasing to positive 1. It never crosses it. So that means that point where it turned, which was at 1, which gave us the point 1, 2, that would have to be the absolute maximum. And then because it's decreasing from negative infinity, it's got to be decreasing from positive 1 because it never will reach it. It'll never cross through that point again. So negative 1, 0 has to be our other point. And you can see the point of inflection occurring. Even though here this is not as drastic as, say, something like that. Even if you think about like a cable that's hanging. If you see only an up close portion of it, it probably doesn't look very concave. But as it's spread out, you will see that kind of concave up shape appearing. Same with the concave down shape over here. And notice that we go, here's a point of inflection. This is another point of inflection. So from negative square root of 3 to 0, we have the concave up part. From 0 to square root of 3. From 0 to square root of 3, we have yet another concave down part. So that's kind of where this is all going to come into play. You can tell a lot about a function based on its first and second derivative, and you can relate the first and second derivative together to get more information. So that does it for 4.4. I think next, I won't say where we're going next because I don't remember if I have planned to go to 4.5 or jump back to 4.2. But it's going to be one of those two things.